Sorry, guys. Oh, that's a very zoomed in version. I moved my my camera yesterday, so now it's all out of whack. Okay, cool. Cool. All right, so we're starting to talk about Chapter 9, which is all about solutions. Now, when we talk about solutions in a chemistry context, we're talking about a homogeneous mixture between usually, not always, an ionic solid and which is called, the solute, and water, which is called the solvent. And I'll write that cuter down below. So a solution has two main components. The solute is the thing that's being dissolved. Oof, not enough room. Sorry, guys. Technical difficulties. Hey, there we go. All right. The thing that's being dissolved, and the solvent is the thing doing the dissolving. Okay. Is everybody comfortable with what the word dissolving means? I know it's a pretty generalizable term. We're all right with that? Cool. So a solution is a homogeneous mixture. What does homogeneous mean? Do you guys remember that from like a million years ago? The same composition throughout, or a uniform composition throughout, right? So a homogeneous solution would be something that you can't tell the difference between the components, right? Basically. Does that make sense, guys? Cool. A solution is a homogeneous mixture, usually an ionic solid. So this is where our ionic nomenclature is going to really come into play. And whether or not you know how to do the ionic nomenclature is definitely going to be something you need to know in this chapter. And usually for our purposes, we're mostly going to be talking about water as a solvent, right? So we're mostly going to be talking about water as being the thing that's dissolving stuff. But that doesn't always have to be the case, right? There are a lot of other things that can be solvents, especially if you guys end up going on to organic. What you'll find is that there are a lot of other organic solvents, but water is by far and away the most common solvent. So, questions about that so far? We're cool. All right, so we want to talk about solution formation. Okay, so how are solutions formed? We have, specifically when we're talking about water and an ionic compound, right? We have water, which has what kind of intermolecular forces between water molecules?
Hydrogen bond.
Hydrogen bonding, exactly, right? So water has these H bonding networks. Oops, bonding. That's literally the second time that I've done that. I don't know if you guys caught that just now, but... and then an ionic compound. What holds together an ionic compound?
Covalent bond?
That's for...
No, sorry. That's a completely different, the other
That's
one.
okay, that's okay.
I'm sorry, because the covalent nomenclature scarred me.
I'm sure you're not alone.
Word. Okay, ionic compounds are put together by something great.
I love this. It's got this. It's right.
Ion.
Ionic.
Bond.
Ionic bonds. Did somebody say it in there? Thank you, Kata. Yes, so ionic bonds, right? So let's say we're talking about something simple like sodium chloride, right? This is held together by ionic bonds, right? Which is really a fancy way of saying opposites are attracted to each other, right? So if we have positive charges and negative charges, they are attracted. Everybody all right with that? Here, I'm gonna put circles around these so that they're cuter. All right? So when you have an ionic solid being put into water, like say sodium chloride, right? What is going to make the sodium chloride dissolve, do you think? Yes, the water will make it dissolve, right? But specifically, what kind of interaction? So if ionic compounds are attracted to each other with these positive and negative charges, right? Then what would make water attracted to an ionic compound?
They're gonna break it together and then combine with other stuff?
So if we have a partial positive down here on water, right? And a partial negative up here on the oxygen, right? It's still these electrostatic or opposite attractions, right, that are going to make the water be able to break up this ionic solid, okay? So I'm going to draw a terrible picture, and you guys are going to hate it, but it's okay. So we have our sodium ion and our chloride ion, right? What part of the water is going to be attracted to the sodium ion?
Oxygen?
Exactly, right? So what we're going to have is the oxygen part of water is going to line up around this sodium ion, right? And what that does is make a little water blankie around your ion, right? So all of these little negative charges, not full, not formal, right, but just partial charges, add up to basically help neutralize this ion when it's in solution. Does that make sense, guys? Yes, Alex. Yes. Can I just, okay, just for a second, can we just talk about how far you guys have come this semester? Like, I think I got a real neg vibe with you guys last time because I was sad because of cheating. But I just need you guys to understand how proud of you I am. You're doing so well. Can you just like take yourselves back for a moment to the beginning of the semester when we were just doing math problems and you guys were like, I hate you and I can't believe I have to do this. And now what you guys are doing, oh, it's beautiful. So please, please Just recognize yourself for a minute, all right? Because you guys, I'm gonna cry now. I'm clearly pregnant. I'm emotional. But seriously, you guys are doing so well. Okay, so these partial negative charges, right, are making this kind of negative charge blankie around the positive charge, right? So when we were talking about Lewis structures, one of the things that we said was that the charges, having lots of charge is not energetically favorable, right? Does it mean that things can't be charged? No, absolutely not, right? It just means that if you have a naked positive charge, like a sodium ion, right, it's going to be a lot more comfortable when it has this blanket of partially negative charges around it. Does that make sense? So we're not saying that these things don't exist, but we're just saying that there's more comfortable ways that they could be, right? So then with the chloride ion, what part of the water molecule is going to be attracted to the chloride?
Hydrogen.
The hydrogen, exactly. I promise you guys I'll have much prettier pictures in the lecture notes, but something like that, right? Again, not super cute, but you guys get the idea. So we have this negatively charged ion and these partially positive hydrogens, right? Those partially positive hydrogens are making a little water blankie around the chloride ion, which helps make the chloride ion more comfortable. Does that make sense? So, this process, is everybody okay if I turn the page? Yeah? Okay. So this process is called dissociation. Okay? Oops, sorry. Dissociation. When an ionic solid is broken down into cations and anions by a polar solvent. Whew, that was a lot of big words. Okay, so when I say a polar solvent, right, what does it mean for something to be polar? That's just a fancy word for asymmetry is one way of putting it. Yeah, go ahead, Steph.
Is electronegativity involved?
There's electronegativity involved, right? So in order to have something be polar, you guys hit both of those points, right? So you have to have polar bonds and you have to have asymmetry, right? So that's very good, awesome. So when we talk about a polar solvent, we're saying that this is something that can dissolve other things because of the fact that it has those partial charges. Does that make sense? So it's the polarity that allows it to dissolve other things, right? Now I just did kind of a no-no, which is I used the term dissolving. Wow, that was really ugly. Kind of interchangeably with dissociation, and they are not the same thing, okay? So, dissolving for us has a very specific meaning. And that meaning is that it's homogeneously combined with a solvent. Okay? So, why am I making this distinction? Because everything that dissociates is dissolving, right? but not everything that dissolves is dissociating, okay? For example, when we have our old friend glucose, right? This is a form of sugar. There's lots of different kinds of sugars, right? But we know that if we put sugar into water, what happens?
It dissolves.
It dissolves, exactly. But what it does not do is it does not dissociate. Oops, okay. It does not dissociate, okay? So what that means is the glucose molecules can be surrounded by water, right? So they can be broken apart from their crystal structure, which is the larger sugar, you know, the little crystals that you get when you put them in your coffee, that kind of stuff, can be broken down into individual molecules, right? So they're broken down into molecules, right? But they're not broken down into ions. Okay? So in order to be a dissociation, there has to be ions formed. Does that make sense, guys? Cool. Questions about this so far? We're okay. So back to our picture of our ions interacting with water, right? These kinds of interactions where you have a polar solvent interacting with an ion are called ion-dipole interactions. So at the beginning of chapter 8 and through chapter 4, when we were talking about Lewis structures, we were talking about intermolecular forces, right? IMFs. So we didn't talk about this one because I think it makes more sense to talk about it in the context of solutions. But this is the strongest of the strong intermolecular forces, right? And the reason why it's so strong is because you have a full formal charge on one of the guys, right? That formal charge makes this attraction really strong, right? Where if you're talking about the interaction between water molecules, it's still very strong, but it's only partial charges that are interacting, right? So the more charge you have, the stronger the attraction. Is everybody okay with me there? Cool. I don't really need you guys to know that part, the ion-dipole definition, but I think it's helpful to understanding the process, right? Questions? We doing good? Okay, cool. So now we want to talk about dissociation reactions. Okay, so I would say that this part, not to discourage you at all, is probably the part that students struggle with the most. But I think if you practice at it, it makes sense. Okay, hopefully. So a dissociation reaction is exactly what the definition sounds like it would be, right? If you have an ionic solid, right, like sodium chloride, a reaction arrow, sometimes they'll write water above that reaction arrow, and then on the other side of the reaction arrow, what we get are sodium ions in the aqueous phase. That's an AQ, not cute, but there you go, right? And a chloride ion, also in the aqueous phase. Everybody okay with me? Questions? So we talked about the AQ when we talked about chemical reactions in chapter 5, but we really haven't talked about it too much since. But what does aqueous mean? What does aqua mean? Agua. Water, exactly, right? So that's where the base comes from. So when we're talking about aqueous, we're talking about things that are dissolved in water, okay? Yes, thank you, Kata. Sorry, I didn't see that. Does that make sense, guys? Coolsies? Coolsies. All right, so let's do something that's a little trickier, okay? How about this guy, right? This is a 3, sorry. Was that your puzzlement stuff? No? You're okay, cool. So what's this guy's name?
I want to say sodium phosphate.
Yay! You did it. I loved it. It was great. Cool. So when we do the dissociation reaction for this guy, right? What ions are we going to get?
Sodium
Sodium. What else?
and phosphate.
And phosphate, right? So this was a point that I think the lab made, but we didn't really talk about too much, right? Which is that the polyatomic ions do not break up when you put them into water, right? So the polyatomic ions, when you dissociate them, the ion stays together, right? So it doesn't break up into phosphorus and oxygen. Does that make sense, guys? That's easily the #1 thing that I see students doing wrong with dissociation reactions, is they really want to break everybody down, right? Now, what's wrong with this equation?
The charge.
Yes, that's part of it. Mm-hmm.
You're not balanced.
It's not balanced. Yeah. How could we balance it? So we have 3 of these guys, right? So when we dissociate an ionic compound, right, this subscript that's telling us that we have 3 sodium ions is now going to come out front. Does that make sense? So just a gentle reminder, this 3 has nothing to do with the charge on sodium, right? Sodium's charge is set in stone. It's always going to be a +1 because it's a group 1 metal and it needs to lose 1 electron to get back to that noble gas electron configuration, right? So we're not changing the charge on sodium ever, right? But in this ionic compound, we needed 3 of these guys, right, to make this guy be neutralized, right, aka have no charge. So when we do a balanced chemical equation, when we talked about this in chapter 5, we said that we have to have the atoms balance out on both sides, right? So whatever we have on the reactant side, we must always have on the product side, right? The same is true for charges. So over here on this side, you guys see that there's no charge. The charge is 0. You guys with me? So if the charge over here is 0, right? Then the charge over here better also be 0. This is called charge balance, okay? So what we do is we have 3 sodium ions, right? Each one has a +1 charge, right? You with me? So 3 times +1 equals
3.
3, yep. And we have, there's no 1 written out front here, but it's implied, right? So there's 1 phosphate, right, which has a -3 charge. So +3 and -3 equals 0. Huzzah. -3 is from this guy, phosphate. No worries, that's fine.
So these dissociation reactions are kind of like, to me, I just keep thinking like, oh, it looks like a decomposition reaction because but it's not. Because it's obviously.
So when we talk about, so you're not wrong. They definitely have a similar kind of format. But when we talk about decomposition, we're talking about breaking bonds, covalent bonds, rather, to be more specific, right? So here, this is a type of decomposition, I guess you could say, but it's specifically, it's such an important type of decomposition that it has its own name, if that makes sense, right? So dissociation is specifically referring to ionic solids that are being broken up. Does that make sense, guys? That's a great, I love that. You guys are connecting things. It's beautiful. I love it. Any other questions about the dissociation? Let's do one more example that's a little bit trickier. Not much. Whoops, sorry. So, the dissociation of this guy, right? What ions are going to be formed?
Calcium plus phosphate.
And what's the charge on calcium? 2.
2 plus.
Yeah. Is everybody comfortable with how we determined that that was a +2? I know it's been a while. We're okay? Cool. And that'll be aqueous. So we'll have calcium ions and phosphate ions. Right? And how do I balance this equation?
Did you not need to put the subscript outside of the phosphate?
That's what I'm asking about. The
Oh.
subscript? Oh, this guy? This too. Ah, so that's what we're talking about, right? So the phosphate is still the ion, right? It's still breaking up. Is it always aqueous? Yes, yeah. So when we dissociate into water, it becomes aqueous. Yeah, absolutely. Does that make sense, Alicia? Cool. So yeah, absolutely, Kata. We want a 3 out front of the calcium, right? And what else?
A 2 for the phosphate?
Yeah, so this little 2 as a subscript is going to come out front of our phosphate, right? So just a reminder, the reason why we have parentheses around the phosphate here is so that we indicate that there's 2 phosphate ions, right? Not 42 oxygens. Does that make sense, guys? So we have to have those parentheses, and one of the reasons why is because when this thing dissociates, right, it's going to form 2 phosphate ions in solution. Does that make sense, guys? Everybody all right with me on that one?
Mm-hmm.
Does this kind of help you guys understand ionic nomenclature a little better? Hopefully. I think for a lot of students, learning the nomenclature in the absence of kind of understanding what the heck these things are doing and why they're doing it can be kind of challenging. So hopefully if it didn't really make sense before, maybe this is going to help solidify that for you guys. So we know that we had 3 calciums on this side, 3 calciums on this side, 2 phosphates over here, and 2 phosphates over here, right? So the next thing we want to check is this charge balanced? And generally speaking, if I've balanced the atoms correctly, then the charges should be balanced also. But we can double check, right? So over here, our charge is 0, right? And over here, our calcium has a positive 2 charge. And there's 3 of them, right? So I need to multiply that positive 2 times 3, right? And then over here, our phosphorus, our phosphate has, we have 2 of them, right? And each one has a negative 3 charge. So this gives us 6 minus 6, which is 0. So we're charge balanced, right? Everybody comfortable with these? Not too bad? I think the hardest thing with these is just remembering that this subscript is going to come out front when we break them up into ions, okay? Cool. All right, you guys ready for a little bit of next level stuff? Let's come back to double D reactions, right? So we didn't talk too much about what was happening in these reactions before, but now that we're dealing with dissociation, we can talk about these in a little more detail, okay? So just a reminder, a double displacement or a double replacement reaction is always going to involve 2 ionic compounds. This is the general form, right? So this is just kind of the general way that these things will look. Hi, puppy. So here A is going to be a cation, right? The first guy that we write in the ionic compound will always be a cation. And B is an anion. And we're mixing it with CD, which is also an ionic compound. C also cation, D also anion, right? And what happens in this double D reaction is these guys change partners, right? So I still have a cation hooking up with an anion, right? And a cation hooking up with an anion. Oof, that was the ugliest arrow ever. But now they're switching partners, right? So the hardest thing to remember about these guys is you always have to make sure that you have opposite charges coming together, right? So looking at the other side of this reaction, we'll have AD, right, which still has a positive and a negative stuck together, plus CB, right, which is still a positive and a negative. Does that make sense, guys? You guys remember this, kind of, sort of? Cool. So let's talk about what this looks like when we have actual compounds, ionic compounds. So let's say we have, anybody remember what that guy's called?
Hydroxide?
Sodium hydroxide. Yeah, totally. Awesome, you guys. So I got sodium hydroxide, and let's do you guys remember what that guy's called? Subscript on, are you talking about this guy? That's aqueous. Sorry, AQ. Yeah, no, that's fine. I'm sorry. No, don't be sorry. My handwriting is really bad, especially when it comes to lowercase. So, what were you going to say, Steph? I'm sorry.
just, going off my gut here. I
Yeah.
want to say silver nitride.
Nitrate. Very, very close. So yes, well done. Yeah, silver nitrate. Awesome, guys. Woo! You're breaking up there, Steph. I think our microphone is sad right now. Okay, so here, and this may be silly, you guys, but I do this for every double displacement reaction because it really helps me. I write the charges of the ions out below them, okay? I know that that sounds trivial, but it's really easy to hook up the wrong ions, right? So I know that this guy is a +1, right? And this guy, again, hydroxide is a polyatomic ion, right? And the whole thing has a -1 charge. You cool? And then here, silver is a +1, right? Now remember, silver was on our staircase. So we have silver, zinc, and aluminum, 1, 2, 3, up the stairs, right? So +1, +2, +3, right? So that's how I knew that that was a +1. But even if I didn't know that silver was a +1, nitrate is a -1, right? So the entire NO3 ion has a -1 charge, right? So if I only needed one of these guys for every one of these guys, then this has to be a +1 charge, right? Everybody still all right with me? Kind of confusing, I know.
So just to clarify real quick, so nitrogen would usually have a -3 charge, and then oxygen has a -2 charge, so it becomes -1. Okay. I'm trying to just dissect because
I know what you're thinking in terms of trying to connect the monatomic anions to the polyatomic, and it's not a good way. Yeah, it's not that. What I would say is the way that these things are charged has to do with ion stability, which is more about the Lewis structure than it is about the actual charges on the individual monatomic anions. Does that make sense?
I'll let it go.
No, it's a good place to go with things, right? But I don't think that it's not a 1-to-1, if that makes sense, right?
I'm just still thinking all the time about like things wanting to get to a noble charge. So
Yeah. So here the nitrate ion, why it carries a -1 charge, has more to do with the ion stability than the individual atoms that make it up. Does that make sense? So it's more about the whole that's formed from these parts than it is about the parts themselves. Does that make sense? And that's a really common theme in chemistry in general, right? Is that, when we see an individual atom and its properties, it has almost no resemblance to the compounds that it forms, right? So carbon has a lot of very specific properties, graphite, diamond, things like that. But the things that carbon makes are tremendously varied in their properties, right? So saying that something is bad because its atom is bad is false logic. Does that make sense? Cool. Cool. That was a good point. Thank you for bringing that up, Steph. Okay, so anyways, back to the double Ds. So we're going to have these guys switching partners, right? So who is sodium going to hook up with?
Nitrate.
So I'm going to have, oops, sorry guys. I'm going to have sodium nitrate, right? And who is silver going to hook up with? Say again? The hydroxide, yeah, exactly. Sorry, I don't have enough room on the page, so I'm going to write it down here. So, couple of things here. Everybody comfortable with why these guys switch partners in this specific order? Cool. And if you guys notice, I wrote a little S down here, right? What does that S stand for? Nothing replaces the water. Sorry, Alex. I'll get back to whatever I was just saying. So you're starting out with aqueous compounds. Nothing's replacing the water, right? So this is essentially all happening in a water bath. Yeah. So it's really, really common to have reactions happen in water that have nothing to, maybe I shouldn't say it that dramatically, but that have very little to do with water, right? The water is definitely like there. It's kind of facilitating a bit of the process, but it's not chemically reacting. Yes, absolutely. So what's happening here is we're forming a solid, right? If you guys can remember back to, what was it, experiment 4, where we were doing separation techniques, and you guys made the silver iodide, the yellow solid stuff. You guys remember that, like 1,000 years ago? So when you form a solid in a double D reaction, it doesn't look the way that we imagine a solid should look, right? Like when I think of a solid, I'm thinking of like my cup, right? I'm thinking of my pen, this kind of stuff. But when we form a solid in solution, it kind of just looks milky, right? We can get the solid that's formed to kind of coalesce via different methods, and some solids that form in in double D reactions are going to naturally make bigger solids, right? But this guy, when a solid is formed, any solid, in a double D reaction, is called a precipitate. Okay? Precipitate. Now, this is the $25 word that I will never write again. We just write PPT. Okay? Well, my daughter is sad. I'm guessing she was being a butthole. So, I don't know if any of you guys were wondering this, or maybe you're like, no, please don't tell me about that, but I'm going to do it anyways. Why is silver hydroxide a solid, right? Or how did I know? And why is sodium nitrate aqueous, okay? So that comes down to a set of rules called the solubility rules. Okay? Solubility rules tell us about what things are going to dissolve and what things are not. It's not soluble, yes. So if something is soluble, sorry guys. I don't know why that word looks really weird to me. I'm spelling it right. That's the kind of day we're having now. Ooh, I'm over time. I'm sorry, you guys. I'll wrap it up. So something that's soluble can be dissolved or dissociated. And something that is insoluble does not dissolve. Or does not dissociate. Okay. So, questions about this?
Yeah, how did you know the silver hydroxide?
From the solubility rules, which we'll talk about in great detail in the next class.
Oh, okay.
Yeah, it's basically just a list of rules that you would look up. There's a couple of easier things to remember, and I'll give those guys to you in a little bit. Okay. So for now, that's the unsatisfying answer. Sorry, Jorge. Any other questions? Oh, no, you would never have to explain these, but you would be given the solubility rules, right? And then you could tell me if you formed a solid. Does that make sense? I probably, I see what you're asking. No. So what I would like you guys to know is what ionic products are formed. Does that make sense? So knowing that that these are the products that form, but not necessarily the phases. Does that make sense? So I don't expect you guys to be able to predict that this guy is a solid on an exam, right? I would give you that information. But how I know that is from the solubility rules. How do we show our work for something like this? Just this way. I'm sorry, I'm not answering your question very effectively. This having a positive charge and a negative charge, I guess, right? I don't want you guys, so real quick, I'm gonna turn this off.